Alright, we're beginning online class 3, section 4.2, basic concepts of probability. We're launching into the probability portion of this course. As you may recall, there's three major portions of the course: descriptive statistics, probability, and inferential statistics. So we're seeking to build a foundation for inferential statistics later on in the course by investigating these concepts of probability, chiefly in chapters 4 and 5. Alright, first thing I want to talk about is some definitions and notation here before we go on in earnest. First of all, an event. An event is any collection of results of a procedure. A simple event. Simple event is an outcome of a procedure that cannot be broken down into simpler events. I'll give you some examples of these definitions in a minute. And perhaps most importantly, a sample space is a set of all outcomes of a procedure or experiment. Let's give you some examples here. Example. Let's have a procedure. I'll label one. Let's roll a die. A standard six-sided die that you'd see in any casino or board game. An event within that procedure is to roll a prime number. A prime number. Now, as we know, the prime numbers, the prime numbers from 1 through 6, 2 is a prime, 3 is a prime, 5 is a prime, and there are no other primes from 1 to 6. So the event 2, 3, or 5 would be an event in this experiment or procedure. Now, a simple event. Remember, from the definition, a simple event is an event that cannot be broken down into other, simpler events. So an example of a simple event in this procedure or experiment would be to roll a 2. Now, we've all encountered probability before in our lives. Well, let's say the probability of rolling a 2 in this experiment. Well, I think everybody in range of my voice would agree you've got one way to roll a 2 out of 6 ways to roll a die, so the probability of rolling a 2 in this experiment is 1/6, right? Alright, let me formally sharpen that definition up a little bit. I'll say for any event A, the probability of A we shorthand that in this somewhat function notation. We use a cap P with an event described within following parentheses. We'll say P of A, or the probability of A, is, well, it's a fraction, really. It's the number of ways A can occur divided by the total number of simple events in your experiment. In the above example, there were 6 simple events, namely 1 through 6, rolling a 1, 2, 3, 4, 5, or 6, and there was only one way to roll a 2, so hence we computed the probability of a 2 in that roll was 1/6. Alright, how about in the same experiment, or the same procedure? Namely, roll a die. What's the probability of rolling a prime number? You can also describe events in words within those parentheses, and I read this left to right as the probability of a prime is. Well, how many ways can you roll a prime? We've already investigated that. There's 3 primes in between 1 and 6, and the total number of simple events is 6, and again 3, 6 is 0.5 simplified. So the probability of a prime in this experiment is 1/2. Pretty simple so far. What I'd like you to do is consider now table 4.1. Alright, so pause just for a moment, and I'd like you to turn to table 4.1 on page 137. Excuse me. Table 4-1 on page 137. All right. Pause now and get there if you would, and take a minute to review that literature on page 137 and also the table. I want us to focus specifically on the table. Alright. Table 4.1 refers to the chapter problem. Every chapter begins with what they call a chapter problem, which is designed to give you a kind of intuitive feel of what's going on and motivate you to study the rest of the chapter. Alright, this table 4.1 on page 137 talks about a lie detector study. Alright, basically there are 98 subjects in this study, and they are cross-referenced in this table in this fashion, which I'll try to copy here. The book does a much better job, of course. Alright. Alright, basically we ask here in the top columns, did the subject lie? And here we say no, the subject did not lie. And in this column we'll file the yeses, where the subject did lie. Alright. Over here we will register the machine results in these cells. Here we're asking, did the polygraph results. Here in this row, for these subjects in this row, the machine said yes, there was a lie. So I'll say the poly says a lie, and for a negative result, now that's equivalent to saying that the polygraph said that there was not a lie from the subject on the particular question. Alright, these are cross-referenced like so. Okay, so again we've got this column represents the people that lied, this column represents the people that did not lie, this top row represents where the machine said there was a lie, and this row said where the machine said there was not a lie. Again, the grand sum of all these cells is 98, so where there were 98 subjects represented in this table. Alright, from this table, what I'm going to do is assume one of these subjects, one of these 98 subjects, is randomly selected. Pick one randomly, and I'll ask you this: find the probability of a positive polygraph result. In other words, find the probability that the polygraph said there was a lie. Alright? I will summarize it like this, symbolize it like this: the probability of a polygraph machine said there was a lie. Alright, well, I claim how many, if we look back on the table, how many of these people did the polygraph say lied? Well, whether they lied or not was another story. In this row, the total of this row is the total number of people the polygraph machine, right or wrong, said lied. So we just add these two cells. 42 plus 15 is 57. So I'll say there's 57 ways to pick a positive polygraph result out of 98 subjects, and I'll divide that out and round off to 0.582. Okay, so this is a common tool in statistics land, breaking things down in what they call marginal tables in this fashion. Alright, let's go on. Let's say we're looking for the probability that the polygraph said no lie. Well, that's really, in the machine language, that's a negative test. Negative test from the polygraph machine, right? No lie, right? So we look up on the table again, and if we add these cells for all these subjects, right or wrong, the polygraph said that they did not lie. And there's 41 of those subjects indicated in that row. So there's 41 ways to pick a negative test result, again divided by a total of 98 subjects. And I'll divide that out and round it up, or round it off I should say, and I get 0.418. And I think you see where this is going. Some of the homework problems are similar to this. We're working out here, what's the probability of randomly picking one subject and finding a liar? Again, we randomly select one. Let me highlight that. We may have lost sight of that in all the text here. We'll randomly select one of the 98 subjects. What's the probability of finding a liar? Well, let's go back up to the table. Alright, now remember, well, what are the liars here? Well, these are the liars. Alright, the sum of this column are the liars in this study. Whether the machine catches them or not is another story, but if we're looking for the probability of a liar, I add 42 plus 9 is 51. 51 liars out of 98 subjects, and I'll grind that out. I'll call it 0.520. And again, randomly select one, and I'll ask, of course, well, what's the one we haven't done yet? What's the probability of finding a not liar? Or a subject that has not lied. Let me go back up to the table, and we'll see this column here is the people that did not lie. Right? And we can see there's 32, 42, 47 of those people. Right? And again, whether the machine catches them or not, that's another story. There's 47 not liars in this study. And there's 98 people total in the study. So I'll just take 47 not liars divided by a total of 98 people, and I get 0.480. And box my answer and go on. Okay? Alright, I'm going to illustrate another example of probability, basic concepts in probability. Let's take a look. Let's say a couple has 2 children. Okay, and let's say we're interested in the probability of one gender or another, and let's assume a boy or a girl is equally likely, you'll hear that verbiage a lot in statistics study, assume boy or girl is equally likely in any birth. Alright? Alright. What I'm going to do here is list this sample space regarding gender in the births of 2 children. Ask yourself, how many possibilities are there for 2 children, allowing any child to be of any gender in any order? It turns out there's 4. Right? Let me list the sample space for this procedure or experiment. Remember, your sample space is the list of all possible simple outcomes in an experiment. Well, I claim the first one can be a boy, and the second one can be a boy. Right? That's one outcome regarding the 2 children. I claim the first one could be a boy and the second one could be a girl. I claim the first one could be a girl and the second one would be a boy. And then finally the second one could be a girl. The first one could be a girl and the second one could be a girl. So these are a list of all the possible simple outcomes for the births of 2 children regarding gender. Boy, 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 girl, girl, boy, girl, girl. Alright, there's another way to do this. It's a little more cumbersome. We sometimes call this a tree diagram. You may have seen this before in your math careers. Well, if I allow for the first child to be a boy or a girl, each of these possibilities trails off to two other possibilities for the second child. And you can see every possible path from left to right illustrates a simple outcome, and the collection of all those is the sample space. Boy, 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 girl, girl, boy, and girl, girl. Alright, takes a little more ink to draw it out that way, but certainly a tree diagram is sometimes available to you. Okay? Alright. Let's ask some specific questions about this procedure. And let me get to another screen here. Hang on a minute. Alright. Get to the top of the screen. Here we go. Alright. Let's say, again, a couple has two children. Let me ask this question. Find the probability of two boys. Right? Now you know there's four outcomes, right? We already talked about that. Four simple outcomes. Boy, 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 girl, girl, boy, and girl, girl, right? Well, you've got four outcomes, so there's four ways to have two children, gender-wise anyway, allowing any child to be of any gender in any order. The probability of two boys, well, let's see, two boys, well, only one of these outcomes has two boys, right? So there's one way to have two boys out of four ways to have two children, again, at least with respect to gender. So I call that 1/4 or 0.25, right? Similarly, what's the probability of two girls? Again, assuming boy and girl are equally likely in any birth, well, you can see there's two girls. There's only one outcome has two girls. One way to have two girls over four ways to have two children, again, allowing any child to be of any gender and in any order. And that's also 0.25, right? The situation gets a little more complicated when you start talking about 3 children, 4 children, 5 children. I want to start talking about that right now. Let's see. If a couple has 3 children, again, we'll assume boy and girl are equally likely in any birth. List the sample space. Now, we could draw a tree diagram here, but it gets a little cumbersome, especially when you get to 4 children, 5 children, whatever. What I'm going to do is I'm going to start out my sample space with 3 boys. Alright, boy, boy, boy is a possibility for having 3 children. Right? What I'm going to do now is say, well, I'm going to change the 3rd child from boy to girl. Right? Basically, I'm going to toggle the gender of this 3rd child. Once I do that, I will toggle the next birth, the 2nd birth, and I'll toggle that from boy to girl, reset this back to boy. So I'll have boy, girl, boy, then boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl. Alright, there are 8 outcomes. Alright? 8 possible simple outcomes with regard to gender when I let any child be of any gender in any order for this experiment for 3 children. All right, if this seems a little confusing to you, don't panic. You'll get the hang of it, I'm sure. Here's a little hint. The third child, if you're reading left to right, first child, second child, third child. Let me put that up here. First child, second child, third child. You'll notice the boy and girl in the third column here, the third column gender changes every time I go down the list. Boy, girl, boy, girl, boy, girl, boy, girl. Notice the second column, right? Changes every second time. Boy, boy, girl, girl, boy, boy, girl, girl. And notice this first column changes every 4 as I go down the list. Boy, 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 and girl, 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 girl. All right, that may be a good guideline to help you figure out the sample spaces, especially when you get to the higher numbers of children. All right, we've got 8 outcomes. 8 simple outcomes for having 3 children. Again, allowing any child to be of any gender and in any order. All right, let me ask a question about this sample space. Find the probability of 2 boys. 2 boys. So I have to look in the above list. See if I can get it back in the picture here. Look in the above list and look for the outcomes that have 2 boys in them. Now, a sticky point may be, well, 2 boys means exactly 2 boys. So I'm going to circle the outcomes that have 2 boys, and again, that means exactly 2 boys. Whoops, I slipped a little bit. There's one. Boy, boy, girl. That has 2 boys. Boy, girl, boy. That has exactly 2 boys. And this outcome. Come on. That has 2 boys. So we'll have boy, boy, girl, boy, and girl, boy, boy. And I believe those are the only outcomes in this list that have exactly 2 boys. So there's going to be 3 outcomes involving 2 boys divided by 8 possible simple outcomes. And 3/8, if you grind it out, is 0.375. Okay? All right, there are some homework problems involving this. Some are as simple as this. Some are a little more complicated. We'll get more into that towards the end of the lecture, or perhaps in our face-to-face class. I want to focus now on example 8 on page 143. So take a minute to pause. And turn there, please. All right. The problem statement, as you've read it, is: will KFC gain or lose customers once they announce the loss of trans fats? Now, based on the data, we've got these conclusions here. Based on the polls here, they say 1,941 respondents predict KFC will gain. 1,260 predict they will have the same amount of customers after the switch from trans fats, and 204 customers claim they or say they will lose customers. Right? 204 respondents claim they will lose customers. Again, the book asks us, find the probability that a randomly selected response from the above pool states KFC will gain customers after the proposed change. Okay? Alright, well, let me summarize it like this. I don't like to be too terribly formal about it, so I'm going to write it out in verbiage here. The probability that 1 says a gain, if we randomly selected 1, right? A randomly selected response, that means 1. The probability that 1 says there's going to be a gain, well, there's 1,941 ways to pick somebody that says there's going to be a gain, divided by 3,405 total respondents. And if you, very simply, if you add these three values here, you'll get the total pool of available respondents, which is 3,405. If I divide that out, I get 0.570. That didn't come out very well. I'm having a little trouble here. 0.570. Unbox it, go on to the next question. Okay? Alright. A couple more things I want to talk about in this section is impossible events. Impossible events have a probability equal to zeros. Alright? The probability of any impossible event equals 0, and certain event, well, if you're considering a certain event, the probability of a certain event, as you might predict, equals 1. And you can't get more sure than certain, so that implies that any probability of any event has to be between 0 and 1 inclusive. All right? So our universe of probability will exist in the, somewhat small number interval between 0 and 1. So anytime you're answering a question about probability, if I ask for a probability on a test or something like that, if you give me a probability that's bigger than 1, you can be sure that it's wrong. If you give me a probability that's below 0, in other words, a negative value, that's wrong also. So that may be a guideline to help you keep from making silly type mistakes. All right. Let's talk about complementary events. Well, we can illustrate this very easily with what they call a Venn diagram. I know many of you have seen these before, even in elementary grades. They seem to be creeping in more and more at earlier and earlier ages. If this rectangle represents our entire universe of available sample space, I'll abbreviate that SS, and if I have an event A, a circle that denotes an event A occurring within our universe of available possibilities, then I claim everything outside of A but included in the sample space is the complement of A, or what we sometimes is called A bar, or what I call not A. So if the probability of A is equal to, let's say 0.7, you know the probability of not A is got to be equal to 0.3, right? Because that contains all the possibilities, all the events not contained in A. The book gives a simple example. This is example 10 on page 145. Let's say we've got a 5-choice, multiple choice question. And if I ask you if you randomly select an answer, and let's say you know nothing about the question and you're just making a wild guess, if you randomly select an answer, the probability that that answer is correct, well, clearly you know what that's going to be. You've got 5 possibilities to choose from. Only one of them is correct, so the probability of being correct is 1/5 or 0.2, right? If I ask you what's the probability then of being not correct, and this is just how I would write it here, probability of this event, correct bar means not correct, well then of course you would say there's 4 not correct answers out of 5 available, and that's going to be 0.8 when I divide it out. Again, clearly you can see the probability of complementary events always has to add up to 1. Let me get a new screen here. Note, the probability of A plus the probability of not A always must equal 1, right? Alright, the book asks us about unusual events. And you may recall we've talked about unusual events before in terms of standard deviations. We've talked about unusual events in terms of z-scores. And now we're going to talk about unusual events in terms of probability. And the book makes this, again, it may seem somewhat arbitrary claim, but again, it foreshadows things we're going to be doing later on in the semester, so it's not as trivial as you might think. Let me write down what the book claims. Events with probability less than 0.05 are labeled unusual. Okay? Alright, so at least for now, we'll say less than 0.05 probability is unusual. Book cites an example here, and this is out of your homework list. This is number 29, exercise number 29 on page 150. They talk about death penalty cases. And in the pool, they do a study of death penalty cases for whatever time period. I think it's something in the order of 10 years past. There have been 795 men suffering the death penalty and 10 women. All right? The text then poses this question. If from this pool, if we randomly select one, right, find the probability of picking a woman. And I can summarize it just like this in shorthand fashion. P of W, probability of W. Probability of choosing a woman is what? Well, it's going to be 10. 10 ways to pick a woman out of what? Well, it's 795 plus 10 is 805, right? 805, and if I grind that out on my calculator, 10 divided by 805, I get 0.012. I'll write that down, 0.012. Alright, the book asks us, is this unusual? Well, yes, of course, it's unusual. Why is it unusual? Because it's less than 0.05. Remember, 0.05, at least for now, is going to be our criteria for unusuality, at least regarding probability. So I claim this is less than 0.5, or 0.05, I should say. So we claim it is unusual. So certainly, in terms of these criteria and in terms of the numbers we were given, we claim it is an unusual event for a woman to suffer the death penalty. All right. One more topic I want to talk about before we call it a day. And really, it's something we've talked about already. Let me get a new screen here. Let's say, go back to the couples having children. Let's say a couple has 4 children. I want to be sure we understand how to generate these sample spaces, because, you know, with 2 it's easy. With 3 it gets a little harder. With 4 we might get a little lost. So I'm going to say, again, assume boy, girl are equally likely in any birth, and I'm going to say list the sample space of all possible outcomes. All right? Allowing any child to be of any gender in any order. All right, now a tree diagram for something like this would be, it would take more space than I have on the screen for you to show you right now. But I can get you started on this, and one of the homework problems does talk about the possibility of having 4 children and ask you about the probability of some cases in this regard. All right, I'm going to, again, make 4 columns. One for the first child's gender, the second child's gender, the third child's gender, and the fourth child's gender. I'm going to start with all boys. Then, all right, that is a possible outcome. When you can have all boys when you have 4 children. And then what I'm going to do, build it up like before. I'm going to toggle that 4th child. Once I exhaust all possibilities in the 4th slot, I'll then toggle the next child up, right? I'll go boy, boy, girl, and then reset this back to a boy, and then go boy, boy, girl, girl. So boy, 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 girl, boy, boy, girl, boy, 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 girl, girl. I've now exhausted all possibilities in the 3rd and 4th slot, so I'll toggle the next most significant child, the second child's gender, to girl. So I'll say boy, girl, and then reset these back to boy and start counting up again. So boy, girl, girl. Oops. Boy, girl, girl, boy. And boy, girl, girl, girl. All right? Now I've exhausted all possibilities in the 2nd, 3rd, and 4th child, and then I can toggle this one now. Girl, and reset these. Girl, boy, boy, boy. Girl, boy, boy, girl. Girl, boy, girl, boy. Girl, boy, girl, girl. Hang with me here. Should be 8 more. Girl, girl, boy, boy. Girl, girl, boy, girl. Girl, 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 boy. And girl, 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 girl. There should be 16 outcomes. Let me count them here. Unfortunately, I can't get them all on one screen. Maybe we can take a quicker look at this in the face-to-face class. If I count them, 1, 2, 3, 4, 5. Let me write them. I do it like this. We got 1, 2, 3, 4, 5, 6, 7, 8. Wait a minute here. 9, 10, 11, 12, 13, 14, 15, 16. All right, there's 16 possible outcomes. You can look at it this way. If let me erase that. If you look at the first child, you've got 2 possibilities. If you look gender-wise at the second child, you've got 2 possibilities gender-wise. If you look at the third child, you've got 2 possibilities. If you look in the 4th child, you've got 2 possibilities. And if I multiply across 2 times 2 times 2 times 2, you know, that's 2 to the 4th power, and that's 16 outcomes. All right? And you can use this list to answer the questions regarding it's number 34 on page 150 in your text. All right, so I'll say C, number 34 on page 150. It's in your homework assignment, and please take a look at your 11th edition solutions manual. Posted on the Lessons tab, of course, on Angel for this course. I'll have this problem worked out with the above possibilities, 16 possibilities listed very clearly, more clearly than I can do it here online. All right? And you'll be able to answer the homework questions pretty easily. Alright, so we're going to call it a day. I'm going to post this video online, of course, and also you will see the reading exercises. Sorry, let me erase that. Reading assignments and homework exercises posted under the Angel Lessons tab for this course under Online Class 3. You'll also see, of course, this video lecture, which you are viewing now, and of course the online exam 3. I'm mentioning this now. Of course, we know that's going to be due when? Let's see, Thursday, 11:59 p.m. on, what's that going to be? Tuesday is 11th, 12th, 13th. It's going to be September 13th. Okay, before our next face-to-face class meeting. So I'll say next face-to-face class is going to be Friday, September 14th, at which time we'll announce formally the test date for our in-class exam 1. Alright, we're at about the 40-minute mark, 41-minute mark, so I'm going to end this, and we'll see you Friday. Please be sure to do your homework and complete the online exam before the appointed time. That is all.